Hello, we'll continue with our lesson on negative feedback, and we are still in the advantages of a negative feedback. We have discussed about 4 advantages of negative feedback. So now we move on to the last advantage of negative feedback. Okay, so a negative feedback will give a better input and output impedance. The input or output impedance can be increased or decreased depending on the type of amplifier used. We have 4 types of amplifier. Each has a different feedback connection. For the first one is voltage amplifier. The feedback connection or feedback topology is voltage series, or it is called shunt series. And then we have a transimpedance amplifier with a voltage shunt or shunt-shunt feedback connection. And then we have transconductance amplifier with a current series or series-series feedback. And lastly is the current amplifier with a current shunt or series shunt feedback connection. So for these 4 type of amplifiers, the input impedance or output impedance can be increased or decreased depending on the amplifier. If you look over here, the output could be voltage or current. It is being fed to the feedback network over here, and at the input section, since it is out of phase, it can be summed either in series or parallel. So the feedback connection type, the first term will refer to the output signal being taken, either voltage or current, and the second term refer to the how the feedback signal with the input signal is being mixed. It is in series or shunt. So we have 4 types of feedback connection. For the first voltage amplifier, so it is a voltage series feedback. So if you look over here, the voltage is taken into the feedback network and it is fed in series at the input. So it is a voltage series for the voltage amplifier. The overall gain will be V out over Vs, the VO over Vs over here. And for the transimpedance or trans-resistant amplifier, we are still taking voltage over here. It is VO is being taken, so the first term is voltage, but this time around at the input section, since you have a current source over here, some of the current going into the amplifier and another is going to this feedback network. So there's a branch over here, so it is called a voltage shunt feedback. Okay, and the overall gain for this circuit is VO over IS. This is a V, this is IS, so VO over IS, V over I, resistant or trans-resistant. Next is transconductance amplifier. For transconductance amplifier, we are taking the current. You look over here, your IO is also the current through IL. It is taken in series over here. Okay, so this is current and it is being fed in series at the input. So it is a current series feedback, or it is called series. And the overall gain is I out over Vs. I over V is conductance. So it is transconductance amplifier. And lastly is a current amplifier, where you are taking the current to the feedback network, and at the input section over here you have the source, which is the current, some of the current going into the amplifier and another branch to the feedback. So at this junction, it is a shunt connection. So you are taking current at the output. The second term refer to the shunt, which is the way it is mixed at the input section. And since it is a current amplifier, so the gain will be IO over IS. Okay, so for each amplifier, it has a different feedback connection or feedback topology. And if you look over here, the beta for each amplifier is also has a different definition. By right, in general, beta is XF over XO. So it could be voltage over current. In this case, it's current over current. And previously, we have a voltage amplifier, voltage over voltage. And for a transimpedance amplifier, we have another, which is IF over VO. So this is the summary. We have 4 types of amplifier. So this is the current feedback connection or feedback topology. So for each amplifier having a different feedback connection, the input impedance either increase or decrease and also for the output impedance it will be decrease or increase. For voltage amplifier, the ideal value it should be infinity, the output impedance 0, but for transimpedance amplifier both input and output impedance is 0, while transconductance is opposite of transimpedance. Both Zi and Zo should be infinity as high as possible, but for the current amplifier it is opposite of the voltage amplifier. For current, the input impedance should be 0 ideally and output impedance should be infinity. So this is gain without feedback. Okay, current over current, conductance I over V, impedance is V over I, voltage is V over V. So now we look into the first amplifier, which is a voltage amplifier. So this circuit is actually amplifier without a feedback. So you have a source over here, your source resistance, and this is input to the amplifier. The amplifier is the one in the square bracket, okay, the dotted line. So you have input impedance, output impedance, the gain AV multiplied with VI, and this is your output, okay. And the ideal value I've mentioned just now, for the input impedance it should be infinity, while the output impedance Z out should be 0. Okay, and the gain, since it is a voltage amplifier, it is VO over VI. And since usually Zi is infinity, so we can disregard Rs. So your Vs is more or less equals to Vi. So Vo over Vs is equals to Vo over Vi. If you look at the input section, Vi is the voltage across Zi, the input impedance. You have a source over here. So if you want to find Vi with respect to Vs, we do the voltage divider. So it is Vs multiplied with Zi divided by the total resistance, which is Rs plus Zi. Okay, if Rs is much less than Zi, because the ideally Zi should be infinity, okay, we can write that Vi equals to Vs because we ignore the Rs. Okay, so that's why Zi must be as high as possible. Ideally it should be infinity. We want all the source voltage will be able to deliver to the input of the amplifier. Vs is equals to Vi. At the output section, okay, the VO is across RL. You have Z out over here. Ideally, for the voltage amplifier, Z out should be 0. You can get the voltage across RL over here by using a voltage divider, which is AVVI multiplied with the load, since VO is voltage across RL, divide by the total resistance over here, ZO plus RL. So it is a voltage divider. So if ZO is 0, meaning that for this equation, it can be simplified to this. ZO is 0, so you can ignore ZO. With this, RL over RL, your VO is equals to AVVI, meaning that why we need Z out to be 0? That's because we want all the gain of the amplifier will be delivered to the load, meaning that there is no voltage drop across the output impedance. So you can write that AV VO over VI is equals to VO over Vs. AV is equals to VO over VI, and it is equals to VO over Vs. So for the voltage series feedback, voltage amplifier, it will employ a voltage series feedback. We are taking output over here, the voltage. So we are taking voltage, the first term over here, and it is being fed right here in series. Voltage series for voltage amplifier. So we want to find what is the relationship between Zi, between the input impedance with feedback and the original value of the input impedance. And similarly, the relationship between the output impedance without feedback with the output impedance with feedback. Of course, for any circuit employing a negative feedback, the gain will be less. So for our circuit just now, we can assure that your Vin over here, it is in series altogether. So using a Kirchhoff voltage law, minus Vs plus Vi plus Vf equals to 0, or we can write Vi is equals to Vs minus Vf. And then Vf is the output of the feedback network. So Vf is equals to beta Vo. Okay, with this, you can plug in the value of Vf equals to beta Vo into this equation. Okay, and at the output section, the voltage Vo is over here. Okay, and assuming that ZO is 0, we can write that VO over here is equals to AVVI. It is parallel. VO is equals to AVVI, assuming that ZO is 0. Since VI just now is VS minus VF, I just plug in into this equation. AV, VI is VS minus VF, and VF is beta VO. Simplifying further, I have VO at the right hand side of the equation. I have another VO, pull it over here, and from there simplify, I will get the gain AF, which is VO over VS. Just rearrange this equation, I get that it is AV divided by 1 plus beta AV. So with a negative feedback for voltage amplifier employing voltage series feedback, the gain will be reduced. This is the disadvantage of having a negative feedback. But if you look over here, if you want to find the input impedance with feedback and what is the relationship to this, we can write using this series between VS, VI, VF. VS is equals to VI plus VF. VF just now is beta VO. Substitute this, and VO is AVVI. Okay, so I just pull out VI, factor it out. So VS is equals to VI in bracket 1 plus beta AV. But at the input section of your amplifier, your VI is actually voltage across ZI. The current entering is II. So I can write VI is equals to II multiplied with ZI over here. Okay, so plug in into this equation, substitute VI with II ZI. Okay, rearrange the equation. We want to find ZIF. ZIF is the input impedance over here. It is by definition, the voltage over here is VS and the current flowing is II. So ZIF is equals to VS over II, and it is simply ZI multiplied with a factor of 1 plus beta A. Okay, so with this, if you look the relationship for voltage amplifier, the input impedance will be increased since ZI is multiplied with a factor of 1 plus beta A. In order to find the output impedance, you have to short circuit the voltage source over here. It is similar to finding Thevenin resistance. You have a voltage source, so it must be short circuit. Okay, so now I call the voltage over here, instead of VO, I call it as V, and the current entering the amplifier as I. Okay, so from this, I can write one equation. V is the voltage at this node. It is equals to the voltage across this output impedance, which is I multiplied with ZO, plus the voltage over here, AVVI. So V is equals to I ZO plus AVVI. With VS 0, okay, we short circuit the input source just now. Your VI will equals to minus VF over here. Okay, so substitute this into this equation. So your V will equals to I Z out minus AV VI. Since we substitute VI with minus VF, so I have a term VF over here, and VF is beta V. Substitute into this. Okay, so V equals to I ZO minus AV beta V. Rewrite the equation. I have V over here. Okay, pull it into one side of the equation, factor it out, simplify. The Z out with feedback will simply, it is looking over here, so it is V, the current is I, so ZOF is V over I is equals to ZO divided by 1 plus beta A. So if you look over here, the output impedance with feedback will be decreased. Okay, since it is Z out divided by 1 plus beta A. For voltage amplifier, ZO ideally should be 0. By employing a negative feedback, it is further reduced. Now we move to the transimpedance amplifier, the second type of amplifier. This is the block diagram of transimpedance amplifier without a negative feedback. You have the source current over here, so you have RS parallel with the source current. Okay, the ideal value for the input impedance should be 0. Okay, while the output impedance is also 0. Okay, and the gain for the amplifier without feedback, it is V over I over here. So ATI, since it is V over I, so it is transimpedance, will equals to VO over II. The current II will equals to IS since ZI is 0. Okay, since it is 0, most of the current IS will flow into the input of your amplifier. So mathematically, we can write using a current divider at this particular node. The current entering the amplifier, it is the current through Zi. You have a source current over here. Using a current divider, your II will be Is multiplied with Rs divided by the total resistance. Okay, and for transimpedance, the ideal value of Zi is 0. Since it is 0, it is much less compared to Rs. So with that, you can ignore Zi. Okay, so with this, you can find that II is equals to Is. And at the output section, you have your Vout over here across RL. Using the voltage divider, VO will equals to ATI multiplied with RL divided by the total resistance. Okay, so using a voltage divider, you can find VO. And ideally, ZO should be 0. With ZO 0, or we say that ZO is much less than RL, you can ignore ZO. With this, then the output voltage VO is simply equals to ATI, which is RL divided by 0 plus RL. So RL cancel out, your VO is equals to ATI. So meaning that with ZO 0, there is no voltage drop across ZO. Your VO will equals to the voltage over here. So that's why we need the output impedance should be as low as possible and the ideal value is 0. So regardless of your RL over here, maybe it is 1 kilo ohm, 10 kilo ohm, it doesn't matter. Your VO doesn't depend on the load value. Okay, so for the transimpedance amplifier, which is ATI, by definition, a impedance will be VO over IS and the value equals to VO over II. So now, the transimpedance amplifier will employ a voltage shunt, meaning that we are taking a voltage over here, feed it to the feedback network, and right here, since it is a source, so the way we mix it, it is a shunt. Okay, the gain of course will be reduced. It can be proven using this equation, AF, which is VO over IS, and IS is the current entering this node, which is II plus IF over here, and IF over here is beta VO, okay, from this definition, and your VO is ATI II, and with this you have II cancel out. So with that, you can get your AF, the total gain with feedback will be ATI divided by 1 plus beta ATI. Of course, the gain will be reduced. But using the negative feedback, we can get the input impedance close to the ideal. The ideal value should be 0. Okay, so you want to find ZIF, which is over here. By definition, Z is V over I. The voltage across the ZIF is the same voltage across ZI. So it is VI. The current through the ZIF will be IS over here. Okay, so we know that IS, the current over here at this particular node, going to the amplifier II, and another is going to the feedback network. So IS equals to II plus IF. Substitute IF with beta VO. Divide everything with II. Okay, V over I, you get V divided by II is the input impedance ZI. So your ZIF will simply ZI divided by 1 plus beta A. Since it is transimpedance, so it is beta A Ti. So with a negative feedback, the input impedance is further reduced. Lastly, for the output impedance, ZOF, in order to find ZOF, we employ the Thevenin theorem. Since the input over here is a current, so you open the current source over here. So your IS will be 0. At the output section, the current going into the amplifier over here is defined as I, and the voltage at the output I call as V. In order to find ZOF, it is V over I. Okay, so what is V? V is equals to the voltage across the output impedance, which is ZO multiplied with I over here, plus the voltage over here, ATI, II. At the input section just now, we have set IS to be 0 since it is a current source. So from this, we can get that II is equals to minus IF. Okay, when IS is 0, II equals to minus IF. And plug into the equation. So your V will equals to I Z out. Substitute II with minus IF. And IF is beta V. Substitute IF with beta V. Simplify it further. Pull the ATI beta V to this side of the equation. Factor it out. So your output impedance ZOF will be V divided by I. And the value is Z out divided by 1 plus beta A. So if you look over here, your output impedance with feedback will further reduce. The ideal value should be 0. Your output impedance without feedback is divided by 1 plus beta A. So I have shown two types of amplifier and what is the input and output impedance for both amplifier. It is either increase or decrease depending on the type of amplifier. Thank you.